Today I'll be discussing remote sensing, starting with some principles, some sensors, just a few, accessing data, applications, and where to learn more about remote sensing. Now, sensors are everywhere. We're only going to talk about the ones highlighted in orange, the satellite, piloted aircraft, and drones. And then there's two types of sensors, passive and active. And the upper part of this slide, we see the sun radiating down onto the earth. This is what is used by passive sensors. Most passive sensors have the sun as a source of energy, whereas thermal IR sensors detect energy emitted by the earth, water, and equipment. So if we have a visible light sensor up here in the satellite, the sun emits a full range of wavelengths, but the blue and the red are absorbed by the grass, the chlorophyll in the glass. Green is preferentially reflected back, and that's why we see grass is green. And down below, the active sensors, they have their own source of energy. A key concept is resolution. And remote sensing data has 4 resolutions for each sensor. Spatial, what is the ground sampling distance? We'll just call it the pixel size. Spectral, what wavelengths are collected? How many wavelength intervals, these are called bands, are collected, and they're represented by individual grayscale images. And how narrow are the collected bands in wavelength? The radiometric is how many brightness levels are collected. The human eye sees around 32 levels of gray, but Worldview 3, that we'll see in a couple slides ahead, collects 2,048 levels of gray in each pixel. And temporal, how often does the sensor image the same area? So we'll be looking at this scale all throughout this talk. And the horizontal bar is always wavelength, starting with the shortest wavelengths on the left and going to longer wavelengths on the right. You can see in the center is what you and I see as visible light. It's just a small portion of the wavelength spectrum for this electromagnetic radiation. As we go to longer wavelengths that you and I can't see, we've got the near IR, we've got the shortwave infrared, and the thermal IR. So together these are the visible infrared sensors that we'll talk about next. Then later we'll talk about the radar sensors. So here we're looking at the visible infrared sensors. Again, the horizontal axis is wavelength going from shorter to longer, but the vertical axis in this case is atmospheric transmission. So you can see the visible light is easily transmitted through the atmosphere, bounces off the feature of interest and into our eyes. So here's the visible range, and as we get into longer wavelengths, you start to see these blockages of light coming through the atmosphere caused by molecules in the atmosphere, and we have these atmospheric windows like at 1.6 and around 2.2, 3 to 5 micrometers, and these are called atmospheric windows, and these are the only places that we can build sensors to detect the light. And if we look at the bottom of the axis, you can see Lidar collects in either green or near infrared. Along the bottom are the different kinds of images. Like a color image just collects blue, green, red, whereas a color IR image collects green, red, and near IR. And these are either multispectral or hyperspectral sensors, as shown at the very top. As we look down at Worldview 3 again, you can see it collects many discrete black and white images across the visible, near infrared to shortwave infrared. And we're going to be looking at the Landsat, which collects 6 grayscale images representing blue, green, red, near IR, and SWIR next. And so here we're looking at the blue band. We're looking at the Salton Sea. This is the water. There's a dredged stream going through. This is the canals over here and the agriculture. So let's look at blue, reflected green light, and reflected red light, and they're all very similar, and yet we can see color when these 3 are combined with blue, green, red illumination, or in our eyes. And then the near infrared is totally different. So you can see this is very healthy vegetation in this field. It's bright in near IR, very dark in red, because that's absorbed by the chlorophyll. And then we have shortwave 1 and shortwave 2, this band 7, which is really good for clay and carbonates. Now we can combine any three to make a color composite. So here we've combined the visible wavelengths, and this is what we see if we were flying over the Salton Sea area looking out the airplane. This is the color infrared. You can see it's fundamentally different, so that bright pixels bright red pixels represent a healthy vegetation. This is total infrared, so this only has wavelengths that you and I can't see. It provides a lot of geologic and environmental information. This color composite uses 2 IR bands and 1 visible. It's very popular because water is colored blue and vegetation's in shades of green. And then we can process these 6 black and white or grayscale images to make new grayscale images. Shown here is a color representation of 3 of those combined. And take your eyes over here to the alluvial fan coming off the hill, and you can see it's red in the area that's not cultivated, but you can see there's red soil in the area that's cultivated. So before the canal went in and these agricultural fields, this alluvial fan had a much larger aerial expanse that we could see from the air. So it'd be interesting to see if the crop yields and soil characteristics are different here compared to, say, over there. Now this is the same axis going from short wavelength to higher wavelength with the Landsat blue, green, red, and then this side is brightness. So we'll look at forest and agriculture. This is vegetation. So you can see in the near infrared very high reflectance. They're very bright, whereas when you go and look at the same feature for red, where the chlorophyll absorbs the red light, it's very low. And then water is continuously low in all the bands, low brightness. So we'll compare this multispectral pattern of 6 bands to hyperspectral. So here's that same horizontal axis with wavelength and the same brightness. And here's our 6 grayscale images for Landsat. MODIS has got more. And then down here we have hyperspectral, where you can have up to over 400 individual grayscale images collected. And so you end up with this very smooth curve with lots of very interesting absorption features. And out here, these are very critical for clays, bitumen, carbonates. And here we've got a stack of individual grayscale images. There could be up to over 400. And we just pulled out 1 pixel looking at water. And you can see the low response for brightness, wavelength going from short to long. We look at the pixels over vegetation. You can see this little bump here is blue, green, red, and this high ramp going up for near infrared because it's a healthy vegetation pixel. And then soil. And soil has really interesting spectral characteristics out in the SWIR range. Now we'll look at a spectral absorption feature. In the upper right, we have Joe Zamudio carrying a hyperspectral sensor and measuring in the field instantaneous fields of view. So he starts off in this country rock, and then he walks towards this relic oil seep, it's tar, and puts more and more tar in the instantaneous field of view. And on the left side, when he's in the country rock, you can see there's no pull down in this 2.3. It's out in the SWIR 2 range. But as he adds more tar to his instantaneous view, it pulls down until he's at 100% tar. It's quite a diagnostic feature of bitumen. We can use this to map all the pixels. So on the lower right, those pixels that have this bitumen absorption feature are colored red. So here we have the oil seeps, relic and current oil seeps in the Southern California area. Now they're doing this with airborne and satellite systems looking at methane. And see, it's in the same SWIR range, but now we're doing nanometers instead of 2.3 micrometers. It's 2300 nanometers. But you can see they're able to trace off methane leaks now, a super emitter in California. The next one's just a picture showing concentration of methane coming off a plume. Remarkable technology, and now there's satellites doing this complemented by Airborne, and so they're really getting a handle on where are methane emissions happening in the world. So now we'll move on to thermal IR, and here we're looking at the Astra system that's been flying for 20 years. It collects 5 grayscale images, and In image processing, we can subtract one from another, we can make ratios, we can divide them, and that's exactly what we'll do with these aster bands to do some geologic mapping. This is looking at a geologic map in Afghanistan. So you've got this mountain range going through here and a couple peaks coming through the alluvium. And this is the kind of map that you can make with this aster thermal IR imagery. And so the blue areas are carbonate-rich rocks, and you take band 13 divided by band 14. Quartz-rich rocks are over here, divide 14 by 12. So it's a unique contribution to geologic mapping. Most of thermal IR, of course, is used for infrastructure and electrical transformers, looking at that and seeing how hot they are. So this is looking at a drone with a thermal IR camera, and you fly the drone. This is a flight path. Each one of these little rectangles is an individual image, and you combine all these images into an orthomosaic. So now we'll move into longer wavelengths. We're out into the radar. So we're out at 5 centimeters to 85 centimeters. And we'll first look at the airborne systems, and GeoSAR collects 2 different wavelengths. A short 3 centimeter, which is the X band, and GeoSAR also collects the P band at 85 centimeter long wavelengths. And you can see there's lots of satellite and even more satellite radar sensors going up because they're all weather, they're day-night, 24/7. And so here we use one antenna to acquire radar imagery at different wavelengths. So this is the X band. It's looking at the texture of the surface along with the water content. And then you go to a longer wavelength and you can see it's really quite different. Down here is reflected green light. So this is what we would see on Landsat. And so you have to be trained to make use of this kind of data, but it's very, very informative if you know what you're looking at, and go out and do some field sampling to verify what the pattern means. You can also use one antenna and collect the radar at different polarizations, like if you take your polarized glasses and rotate them, or if you have a camera lens that's got polarized, you can see how that changes the incoming light. And so here we've got a drone flying over an island. This is just to demonstrate the drone can see this boom that shows up in a high resolution aerial image. And on the right side it's doing a great job of picking up the oil and also oil on the beach. You can use 2 radar antennas to generate a digital elevation model. So here we have the space shuttle with baseline that goes out to another antenna. So there's an antenna here, an antenna there. You transmit the wave out of here and it bounces back. One antenna gets the return wave here. Another one, a time delay, gets it over here, and that's how you can build the digital elevation model. Or you can fly satellites in tandem and build a DEM. So here's an example of that GeoSAR aircraft with its 2 radar antennas. And here we've got the X-band radar image. So we're in a forested area outside of Fairbanks, Alaska. And you can see the roads are cut into the forest, and you have clearings. And the next one is in the center is the digital surface model. So the 3 centimeter X band bounces off the top of the canopy, and this is actually the top of the canopy. And then on the right side is a P band, which is longer, 85 centimeters. It penetrates the canopy and bounces off the surface of the Earth. And so we have a profile northwest to southeast, and the solid line is the 3 centimeter top of canopy. And the dashed line is the bare earth. And so you've got a biomass reading, and you see these 2 openings in the canopy. And if we look up here, you see them on the northwest profile line. So the USGS has flown tremendous areas in Alaska to build a valid map of what's going on the surface and what's going on with the biomass. And finally, you can use 2 radar antennas for ground deformation. It's called interferometry. And here we're looking in West Texas at an oil field. And just keep your eyes on L, M, N, and O. And these are the points that were measured by the radar satellite through time, 2015 to 2017. And it detected a cumulative vertical deformation subsidence of over 4 centimeters. And so this bottom graph shows the time 215 to 217 along the horizontal axis. The left axis is the deformation, the left vertical axis, and the right axis is the oil production. So you have these bar graph going down, that's showing the production, and the monitoring with the radar satellite shows these points, L, M, N, and O. As the field is being depleted, you can see that the ground is subsiding. And then at the end, there's some earthquakes. This is now a huge enterprise for looking at infrastructure, construction. I mean, it's being used everywhere. As the radar systems become higher and higher resolution, and the algorithms get better and better. There's other technologies used to generate a DEM. Very accurate, detailed DEMs are produced by terrestrial Lidar and radar. You can also take a balloon and move it around some object on the ground and use structure from motion to build a 3D model, or you can fly a drone and do the same thing, have a flight program that looks at this feature of interest from multiple angles, multiple viewpoints. It's called multi-ray photogrammetry, and you build a 3D model. Terrestrial LiDAR is used all the time to build really detailed 3D models, and now this structure from motion is using it for buildings, geology. It's just exploding. You'll see more examples in this presentation of what it can do. And then we'll look next at LiDAR, and it measures the time it takes for a light to go and hit the ground and come back. It builds very detailed topographic and bathymetric maps. So here we'll look at the LiDAR for topography. It uses the near IR sensor. So this is a map on the left made in 1944 of the Mississippi River, and you can see in the center the narrow stream going through, cut off those big meanders. And on the right side, 75 years later, National Geographic, you can see how that center area, center stream has grown. And also overall, the whole system is migrating south, the meanders. And this is LiDAR for bathymetry. It uses a green light laser that penetrates the water. And you can see it's more complicated because it gets refracted when it hits the surface. But in the end, they've corrected for these in a remarkable bathymetry map with a water depth down to 20 meters. So let's move on to accessing data. Why search for and process data? If you start a project, you really should always go to Google Earth first and just see what's out there. But if you take the time to download the same image or a similar image and you process it, you're going to find that you'll make a more informative image for what you want to find. So here we're looking zoomed in at the Benway Trough on Google Earth at a Landsat image. There's a very overwhelming footprint of agriculture on this scene, and we've got the stream running down here in dark green, so it's a natural color image of 2018. I downloaded a 2014 image. I'm looking for geologic structure and I can't see anything. I just see a lot of these fields that are obscuring my ability to see any structure. But if I go back in time, I go back to 1986 and I process it as color infrared, you're starting to see the geologic structure before mankind came and completely overwhelmed the surface with the agricultural footprint. This is useful, of course, for not only geology but hydrology. So consider historic imagery when you start any project. Another example is in Indonesia. Here we're looking at a steam flood project. The red arrows point to roads and infrastructure that are continuous as we go back in time. So we used georeference, the older image. And then the green points to areas in the upper left and on the side that are totally covered with green. So you would think there's nothing there, there's nothing ever there. So let's go back in time to 1979, and you can see that where the green arrows are located, there was well pads and access roads and oil pits. And you can go back farther in time to 1966 and see this area wasn't developed. We have clouds here, so we don't know what happens there. And here both sides weren't developed. You can say, okay, all this infrastructure was built by 1966, 1979, and a big change by 2014. This is looking at a high-resolution natural color image from QuickBird satellite. If you do your own processing, you can come up with something like this. It's more informative. So I encourage all of you to think about doing your own image processing or get someone to do it for you. So let's look at accessing data. Where's the data? Well, it's everywhere. So we have government, commercial, and scanning. So you can scan your own maps and put them in the system. So in the center we have the data, and you're the user. And now you have so many options. You can do web-based subscription software, desktop software, mobile, and you choose what kind of software you want, the hardware that you can afford. If you're good, you can program and make things way more efficient. And the objective is to build informative remote sensing products. And all of these always have to go into a GIS to be useful. But now you can also do the searches and do the processing with cloud-based services that come back and provide those products to you. So let's first search and download from government agencies and commercial search engines. So here we're looking at the USGS Earth Explorer system, and I'm out in West Texas, and I'm saying, I'd like to get a really up-to-date, moderate resolution image that gives me an idea what's happening down here environmentally and as far as infrastructure. I think I'll search for a Sentinel-2 from the European Space Agency. Of course, they have a huge number of different data sets in this search engine. And there it is, my Sentinel-2 footprint. It was acquired on the 14th of July, 2021. And all I have to do is push this little button with the green arrow. It'll be downloaded to me, and I can process it and put it into my GIS. The European Space Agency has a huge Earth observation program, and they've put up these Sentinel satellites that are just remarkable. So Sentinel-1, there's two of them, and they acquire radar data. They build images, DEMs, and really monitored ground deformation from earthquakes, buildings sinking, you name it. It's heavily used. Sentinel-2 is a lot like Landsat, a multispectral sensor, but it collects higher resolution, higher spatial resolution data, 10-meter pixels in the visible near infrared. And then Sentinel-3 is ocean focused, and it does surface temperature, ocean color. They're really good and free satellites. The Japanese provide global radar data from their pulsar system. And NASA has this Earth data site, which is very sophisticated, huge number of really interesting scientific imagery. But I tend to just go for the nighttime and daytime astrothermal IR data. So I like the nighttime because if I'm over a desert area, I want to know if there's thermal anomalies. And if there's a warm area on a cold night, it might indicate near surface groundwater resources. So you also use it for urban heat islands and just detecting areas that are hotter than surrounding areas. Now we'll move on to commercial search engines. I only talk about the three big ones, but there are many, many more commercial satellite providers. And this is Airbus DNS, and it's like an equivalent of Boeing. And you can see the huge number of satellites that they have up in orbit. And I'm doing a search now in Vietnam. It provides a little thumbnail acquired on May 8th, 2021 with a 1.5 meter spatial resolution. Maxar has very high resolution satellites. Worldview 3 was discussed by Dan Taranik. He gave some incredibly good geologic and environmental applications using this unique satellite. It collects 8 and 16 wavelength bands. 16 bands for visible, near infrared, and SWIR. It's the only one in the world that does that. And the size of these satellites, they're the size of school buses, so they're very high end. And like I'm doing a search now in Port Arthur, and you can see the kind of information you get. It's Worldview 2. It's got 8 bands. There's no clouds. Pixel size is 57 centimeters. And then finally we look at Planet. And Planet is unique business plan in that they launch microsatellites. They're about the size of a shoebox. And they've got hundreds of satellites orbiting the Earth. They call them doves. Each one's a dove. And in the lower right we have a representation of doves colored by their flock. So they're really getting a phenomenal inventory of images of the world. Now you don't have to do your own searching. I've got 2 examples. The Satellite Imaging Corporation will do the search for you. And what I like about their site is they have a very uniform and very informative resource for, okay, I want to know what SkySat 50 centimeters is all about, or I want to know about the new Pleiades NEO satellite, and here it is. It's a really good explanation of the satellite, and they have examples. Another service is Apollo, and so you just define the area, and they go out and search the imagery and come back with what's within your parameters. And what's amazing is they look at 54 different satellites. So, 115 million plus images. And to look at their search engine, this is an example of how you filter. So you can pick a data range for the imagery you're looking for, the cloud cover, whether it's off nadir or near vertical, and the resolution. And if I slide this down to 2 meters, and I'm just looking for imagery that's 2 meters or higher resolution. And I can say, I only want stereo, I only want color. And you can see when I started, there was over 9,500 images in this box in West Africa, in Nigeria. So instead of doing the search and download, you can use cloud-based streaming services to bring the imagery into your GIS or into your mapping system. So I'll just show L3 Harris, and what they do is, here's the big three, Airbus, Planet, and Maxar, and they stream all three if you want into your system. So that's a really convenient way for those companies that need to keep up with what's happening all the time in their area of interest. Esri has this remarkable living atlas which streams all sorts of data, geospatial data, into your GIS. And I'm only highlighting imagery. And what's really good now is the agencies, especially in the US, are now putting their authoritative maps, fish and wildlife, USGS, into the Living Atlas. And so here, remember the Sentinel-2 from ESA? I can download that. Or here's some more. I can download Landsat. So I've done that. So the next image, so I've downloaded some of these layers into my GIS. So here's my GIS, just happens to be ArcGIS Pro. And here's the Landsat I brought in West Texas, the 10-meter Sentinel. And then I downloaded 3 more, the Esri brand new 2020 land cover. So these green areas are trees, the red areas are built up areas, and then you can see that the faint blue lines, that's their USA roadmap, and then I put on top of that contours. So I didn't have to do anything. I just said download these, and I've started a GIS database for my area of interest with these cloud-based streaming services. And now don't forget about historic maps and charts. If you're overseas, really search for what did the area look like before. You might have new and informative information on geology, on environmental conditions. It's essential. And it's very easy to do in the US. Overseas, you have to go to different companies to find the old stuff, scan it and get it into your GIS. And finally, cloud-based processing services. I only show one example. I'm out here with my drone, and I had this flight program I designed for flying over a forest, and so I did it, and it's 165 images. It's got 2 centimeters spatial resolution. All of these are overlapping. The objective is to build a digital surface model of the top of the forest, top of the trees, top of the buildings, and an orthomosaic, a mosaic that's seamless across the whole area that is made up from these 165 images. And so I upload my images to one of the services like Map Made Easy, and they put my flight program into their system, and you can see the center points or the centers of all the images I collected, and they have the horsepower, because I don't. They have the computer horsepower and the software to build the DEM and to build the orthomosaic and download them to me, along with other 3D products for a really reasonable cost. I mean, it's almost free. It's incredible. And so here it is. I downloaded the orthomosaic, and this has got 2 centimeter resolution, so it's a really highly detailed image. And then I can also download the DEM that they process for me, and I've got buildings and trees and elevations for any feature on that. So again, it saves an enormous amount of time and resources to use these cloud-based services. As long as you look at the data after you get it to see, oh yeah, is it what I wanted? So finally, we'll look at applications. Mostly it's on the engineering side, and at the end we look at environmental and geologic exploration. So this is a very interesting company, Keltbray. They're employing a drone for overhead line and substation inspections. Example of the drone they're using with multiple sensors, and they put on this one drone a wide angle camera, a zoom camera, a thermal camera, and a laser rangefinder. And the optics are so good that they're 260 meters from the lines, and this is a spacer highlighted by that red circle that they can see. And now we're going to fly in and do the inspection on the insulator. And in the top image is what it looks like. They can get really close and do a great job inspecting the hardware on these very tall towers. At the same time, they can use their thermal camera. In the lower right, we've got a color image. But with their thermal camera, they can see there's an overheated cable joint that they need to correct. And then with their laser capability, they can make a digital elevation model of the lines. And the most important thing today, especially with the wildfires occurring out west, is to measure the distance between the power lines and vegetation and buildings. So here's like a profile, and they can measure it out. Of course, PG&E and these power companies out west got these enormous problems with the lines causing fires when it gets in contact with vegetation. So I just read PG&E is thinking of burying 10,000 miles of power lines to avoid that tremendous problem. Another interesting application is building footprints. So you can do it by hand. I was involved in a project. We digitized 31,000 buildings by hand, an extraordinarily high accuracy rate. It was, had to be over 99.9%. But of course, that took a lot of time and money. But it was important for that application. But most of the time, it's not that critical to get such a high accuracy. So Esri's got this deep learning model now that extracts building footprints from high resolution aerial and satellite imagery, say 10 to 40 centimeter pixels. The average precision score is 72%, and it is computationally intensive. You got to have a really powerful CPU to do it. Of course, you need the software. The most important thing with this, it looks very neat. Ensure that you look at the data before you send it out, because I discovered, it's missing these footprints. So all you have to do is finish the job, put in these footprints, and you've got a really good product going out the door that didn't take nearly as much money or energy as hand digitizing. Another application, construction volumetrics. So here we're building a digital surface model using the structure from motion technique with a drone. We're going to look at the southwest pile. Here's the southwest pile. We can come up with the area that's covered, but also the volumetrics because it's a 3D model. And this is type of flight program over these stockpiles that they're flying. Each one of these little triangles represents, there's an image in there, an overlapping image, and then you do a circular patterns to get even a better 3D model. Lower image is just a beautiful 3D rendition. It's a visualization of one of these models showing the piles of material that can be very accurately measured. Another application is monitoring as-built progress. So the red and blue lines are CAD map infrastructure, and they're very accurate. The background image is a high-resolution drone mosaic, very high resolution. So this company, Mortison, weekly images their 500-acre construction site, 1,200 to 1,400 images per survey, and they use the Pix4D cloud technology to turn it into a weekly up-to-date image. And it's all for safety. So they monitor the construction activities by superimposing the CAD map of utilities, which include gas lines, on the weekly construction map and make sure that they're avoiding the gas lines and other essential utilities. Another application is building information modeling, BIM, and scanning to BIM. So nowadays, as people are building anything, they're scanning it and they're building this digital record of what it looked like, and it's becoming so high quality that there's companies now that are trying to say, okay, we can find out of spec work early. So they can verify the accuracy of as-built construction against design model using the scan data. So here's an example from Verity that the green in this lower right addition, the green is installed to tolerance, green features. But the yellow features are out of tolerance and the red features are missing. So it's finding out of spec work early. It's going to be a huge industry. Another application that builds on that is build and maintain a digital twin. So a digital twin is you've got your brick and mortar construction development going on. At the same time, you're building a digital replica, and remote sensing and GIS are very critical to that digital replica. So in the upper left, we have the CAD design model that's guiding the construction. And in the lower right, we have the drone as-built model. So you can see the trucks are out front. Now what's really remarkable, if you do this continuously, you can go back in time. So here we are in July 2019 and when they're putting in the first floor. And then we can go back to February 2019 and see when they're clearing. So this digital replica enables you to monitor construction progress across the project's life cycle. And it can just be one well site. It can be anything. It's just amazing building a digital twin. Lidar is an incredible tool. This is an example from the Central California and Pleasanton. And the digital surface model is the upper right. It's the top of canopy, top of buildings, and if it's bare earth, if it's open space, and it's the top of the earth. And in the lower left is a digital terrain model, otherwise known as a bare earth. So the upper right, you can see we can analyze the tree cover, the building footprints, and all these really help build a land cover land use map. In the lower right, once the analyst strips off all the buildings and trees, now we've got excellent map to do drainage studies, to do parcel topography. You can see in the upper part of the DTM these cut and fill slopes. You can plan your utilities, and of course landslide susceptibility. Another big use of remote sensing is change detection. So we've got an air photo collected in 1959 on film. We scanned it, georeferenced it to the image on the right, which is a 2000 ortho image. The yellow arrow points to a structure on the Shell refinery in 1959, and in the 2000 you see there's no evidence it was ever there. The orange arrow points to 4 oil tanks, and in 2000 there's at least 4 tanks, maybe not the same ones, but they're in the same location. And then the blue arrow shows a wetlands full of vegetation with a dredged channel down the middle, down the meandering stream. And what happened by 2000, 41 years later, there's no vegetation. It's all ponded water. So change detection using aerial imagery, satellite imagery is hugely important. This is where we're looking at documenting the environmental impact of accessibility. So we're in Ecuador looking at different licenses for exploration and development. The study concluded roadless and controlled access licenses had far less impact on the natural environment compared with a license that allowed public access. So here we're looking at a license in the upper portion that was public access. You can see all the roads put in over the years, and 2 areas that are pointed out as protected by the government stayed roadless for the most part. License 16 and 14 in the central right part had a controlled access point on the Rio Napo, and you can see there's only that one main road to support the development and a couple coming in from the west. And then the lower right is a helicopter supported development. It's roadless. And so working with the government to say, okay, we're going to keep this roadless, we're not going to allow roads in here, is a big deal. So we'll take a quick look at geologic exploration. This is in Tanzania. We're looking at a digital elevation model from the space shuttle. One of the things you can do in exploration is a drainage map. And so you're looking for drainage anomalies or some sort of break where you can tie the surface into what's happening in the subsurface. You can also make a map showing the faults. So in this area, I interpreted faults looking at the imagery in stereo. And we'll zoom in on this area. And as you can look at this slide with red-blue glasses, anaglyph glasses, and you'll see the pronounced topographic breaks along. They're not really pronounced, but they are topographic breaks that I mapped. And then after the project was over, they showed me the subsurface map that's based on Aeromag and satellite, and it's just remarkable. What I saw at the surface actually correlated with what's going on in the subsurface. That's a really big deal, and it doesn't happen very often, at least not in my experience. So it's very exciting when you can tie the surface into the subsurface. Another application is just looking at what's happening to the environment. And this is with natural gas development in northern Pennsylvania. See, the yellow is the McKean County. And the USGS is looking at the spatial effects of roads, well pads, and pipelines on agricultural fields, on forests, on streams and rivers. And this is the map they developed. So we're in a county, we pull out this area. The green is forest, the yellow is agriculture, and the black is the new land class called gas extraction disturbance. And what they discovered, among many other statistics, is that pipeline construction was the source of most force fragmentation, force loss, and increase in edge force. So for those people that are into pipelines, if you're trying to avoid damaging the force, impacting the force, you want to pay attention and do some really good GIS mapping to minimize that risk. Another application is monitoring habitat. In this case, we're using airborne thermal IR imagery, looking at surface water temperatures, with the objective being to map cold water refuge for fish. And so here we've got the thermometer. When it's cold, it's dark purples. When it's warm, it's yellow, and you can see these cold water refuge. And so if you're doing development here, you don't want to mess with these. And so this is, in alignment with the latest ESG initiatives to look at the environment before you start doing your development. So now that we've seen all these different applications and how to access data, maybe you want to learn more about remote sensing. And you can search the internet. Just go on YouTube and search for remote sensing tutorials, or be a little more coherent and go with, like, ArcGIS has got a program, the Canadian Center for Mapping, University of Minnesota, Berkeley, NASA, and Coursera has remote sensing courses. And I really encourage you to sign up at your local college so you meet people interested in the same things you are. There's certainly GIS courses, and on occasion you'll find a remote sensing course. You could also just read a remote sensing textbook and use the supplemental material, such as, well, here's this textbook that I just authored with Floyd Sabins. We published it in April 2020. Remote Sensing, Principles, Interpretation, and Applications. You can evaluate it on Amazon for $15.69. The differentiator is it has a lot of open access downloadable material to support image processing and learning outside of the textbook. It's structured to support self-taught students. It's published by Waveland Press. This is just looking at the many chapters. The first 10 are on technology, and it covers the latest, like Lidar and DEMs and drones and renewable resources and climate change. One of the supplemental materials is this downloadable remote sensing digital database. It's 6 gigabytes in size, so it's 27 examples. You can download Landsat and work with it. It shows you the in a GIS what it looks like in ArcGIS desktop. The imagery will work in any software. It's got high resolution data, WorldView 3 data. It's got Sentinel-2, Aster thermal IR, radar data, hyperspectral data. So it'll be a lot of fun to work with. Gotten some good feedback on people doing their image processing with this data. The other thing besides the textbook, which is here, which is a good deal in itself, is I built lab manuals with data. The data's examples that are shown and described in the textbook. So I built a lab manual for Envy, which is a very high-end image processing software package. But over the COVID lockdown, I said, most people use ArcGIS, and it's really difficult to do remote sensing and image processing because the menus and tools are all over the place. So I wrote a lab manual initially for ArcGIS Desktop, and then I wrote one for the newer ArcGIS Pro, which works on your desktop and very much tied into the internet. And then when I got done with that, I said, I should participate in the social media world. So I put the ArcGIS Pro, the 12 exercises, on a YouTube channel. And so here's my YouTube channel with the 12 exercises that provide you an overview of all the steps that are involved to, say, do supervised classification or to do heads-up interpretation. And so this is designed for GIS users who want to do their own image processing, enhancement, and information extraction using their desktop ArcGIS Pro software. So that concludes this overview of remote sensing, the sensors, accessing data, applications, and where to learn a little more about remote sensing. So if you have any questions, just please contact me with my email. Thank you.